Hello, good afternoon, and welcome everyone, members of ICTS, members of the program currently going on, and other members of the public, students, and so on. Welcome to ICTS. If you have not been here at ICTS, we are a research institute in the mathematical and theoretical sciences, very broadly speaking, and we have a large number of research activities, including workshops, and of course a lot of outreach activities. And today this is a very special outreach activity for ICTS, and it is something that's also interwoven with our program that's going on, currently the mathematics program going on enumerative methods, which Professor Uri, the speaker, is also a part of. So we use the opportunity to have this very interesting, what promises to be a very interesting event, which is a combination of a lecture and performance. So let me very briefly introduce the speaker and the artists. So the lecture, as you know, is on rational and irrational numbers, strings and harmony, or the story of the equal temperament. And the speaker, Professor Uri Onn, is a professor of mathematics at the Mathematical Sciences Institute of the Australian National University. He graduated from the Technion in Haifa and held postdoctoral positions at Amsterdam, Paris, Mumbai, and Jerusalem. He later joined Ben Gurion University as a faculty member before moving to the ANU in 2017. Beyond mathematics, he has a keen interest in jazz and cooking, and we'll at least maybe hear something about the jazz, if not the cooking. And accompanying him are three very bright, young, musically talented folks, two of them from ICTS itself. So we have on the guitar Shubhadeep Chakraborty, our very own student, second-year IPHD student, currently working actually with Abhishek there. And Shubhadeep has been playing the guitar for 6 years, I believe. So please give them all a big hand. We have Sayantan Mandal, who is an LTVSP student. So ICTS has these long-term visiting student program of students who come for a one-year-long research project. And Sayantan is working currently with Professor Sumati Rao in condensed matter physics. And he has also been playing the piano, and coincidentally also for 6 years. So Sayantan. And finally, we have Michelle. I'd like to welcome Michelle to ICTS, Michelle Simon. She is a final year BSc physics student, again, a student at the Azim Premji University in Bangalore at the other end of town. And Michelle has been playing the cello for 9 years, so a kind of rational multiple of 6, I guess. We'll hear more about octaves and multiples. But Michelle, welcome and thank you. And so finally, let me invite Uri to come over and deliver his lecture and the concert. So please remember, since especially music is involved, please take this moment to keep your phones on silent mode. Let's not have any embarrassing rings in the middle of the event, or especially the performance. And there will be a break in between. The program will last till 6:15. We will take questions right at the end. So please hang on to your questions in the meanwhile. So enjoy, and Uri.
Thank you. Thank you very much, Alice. Good afternoon, and welcome. What I want to talk about today is about equal temperament. And this is, in a way, a solution to a problem that existed for more than 2,500 years, and deals with how and why the 12-note tuning system that is widely used, how it came to life. There were many attempts to kind of solve this problem. Musicians, mathematicians, composers, instrument builders. There's a serious problem in tuning, as we will see soon. And eventually it was solved with equal temperament. But as it happens sometimes with problems, it's also difficult to precisely define the problem. So we'll talk about that as well. Can you see, or maybe we'll make it a little bit darker? So what is the equal temperament? I can tell you in one line. The equal temperament, these are 12 notes equally spaced in an octave. That's it. And that's the topic of the lecture. But it's not so simple. So the first question is, why 12? And what does it mean to be equally spaced? I mean, if you look at the keyboard, or if you look at the staff, it doesn't really look equally spaced. So what does it mean? And what is an octave, and why is it relevant to the story? So these are the questions that we are going to talk about. In passing, we will answer a few other questions that will come up. Let me give you the plan for this talk. This is not an historical account. In 2,500 years, people all over the world doing things I'm not capable to give you. I don't think if anybody can give you an account of exactly what's happening, where and when, in regards to this topic. But I will follow some timeline. It will help me to align the themes of the lecture. So we have four themes or four parts. The first one, we will look at the rational and irrational numbers. And as a pointer, I'm putting the Pythagoreans. Again, many things happened in many parts of the world, but that's just a marker. The second thing that we look at is a little bit of physics and a little bit of wave equations and what's the physics behind musical tones. Combining with these two, we are going to solve the problem and understand the issue of the equal temperament. Then we'll take a break and we'll go back, and the emphasis will be more about music. We will see what can we do with the equal temperament. So we're working hard to get the equal temperament. What can be done with that? And the theme will be kind of symmetry and harmony. It's a combination, as you will see, of what you can do with symmetry and with harmony. In the fourth part, it's just a personal choice. We will take few musical pieces from kind of Baroque area, just to have a flavor of what was done pre-equal temperament. And then we'll jump to talk a little bit about jazz, where we will see the full extent of the equal temperament and what does it give us. So that's the plan. And let me start with a warm-up. Now, the video here is the quality is not amazing, but the video itself, the event is amazing. This is Bobby McFerrin in a World Science Festival about 15 years ago, talking about the pentatonic scale.
Watch. Ba, 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 okay. ba, ba, ba. Ja, dum, da, 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 ba, 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 da, 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 ba, ba, da, 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 ba, da, 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 ba, 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 da, 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 ba.
Yeah. Now, what's interesting to me about that is, regardless of where I am, anywhere, every audience gets that. But it doesn't matter, you know, it's just, you know, the pentatonic scale for some reason.
The pentatonic scale for some reason. So we'll come back to the pentatonic scale later on, and we'll try to understand what's the reason. Why? How did they all know what to do? We'll revisit that. But let's start with some rational and irrational numbers. So we start our way as kids, and when we count sheep, we can count coins, we have the natural numbers. But that's not enough, right? In real life, we have situations where we need fractions, otherwise we can't eat pizza. Three kids trying to eat a pizza, well, I don't know, if you gave a kid a third of a pizza, that can turn up very, very, very messy. But luckily, we can represent fractions in different ways. So we can divide it to 6 and eat 2 parts each. That's less messy and the same content in the end. And so we can have different representations for the same fraction. And now let's take an excursion into the Pythagorean garden, because they were fascinated by the rational numbers. So a rational number is a ratio of 2 whole numbers, 2 integers. And you can do many things with them. You can take 2 rational numbers, you can add them, and you get a rational number. You can multiply them, and you can get a rational number. And you can take the ratio between 2 rational numbers, and you get a rational number. And the Greeks, they believed that the whole universe is built from rational numbers. They saw this in architecture, in everywhere, in mathematics, and also in music. They noticed that if you take 2 strings, and if they have small, if the ratios is small rational numbers, small in the sense that the numerator and denominator, they are small numbers, then they sound harmonious, they sound good. For example, if we take the ratio of 2 to 1, then we get the octave. So Michelle will now demonstrate now the octave. In fact, our ears, they identify tones that differ by an octave. We really hear them as the same thing. Another interesting, and by the way, the name octave is coming from, when you look at the piano, it's the eighth note. So that's the name. And we also have the fifth, which is the ratio of 3 to 2. And Michel will demonstrate that now. Beautiful, right? As the dodo says, the best way to explain something is to do it. So we are going to do it now. You will help me. Let's do an octave. Ready? Ba. Ba. Now together. Ba. Beautiful. Octave. Let's do the fifth. Ba. Ba. Sounds good? These are the two anchors. These are the two main intervals that we are going to use. Now, a natural question, which we are going to answer a bit later, is why? Why these ratios, these rational ratios, why do they sound good? So that's coming later on. But first, let's walk a little bit more in the Pythagorean garden. So they were interested not only in the rational numbers of arithmetic, they were interested in geometry. And for example, they took there were 2, 3 cities or 3, you go from point A to point B and from point B to point C, 4 units and then 3 units, and then it's a perpendicular between AB and BC is 90 degrees, and they discovered that the distance between A and C is 5. And the question was, what's the relation between these numbers? And they found more triangles with this property, right-angled triangles. In fact, they found infinitely many, and they are known as Pythagorean triples. And they noted that they satisfy this relation that the squares of the sides, the sum of the squares of the sides is equal to the side of the hypotenuse. And actually they thought maybe it's not an arithmetical issue, maybe it's a geometrical issue. And indeed, they proved the Pythagorean theorem that in a right angle triangle, the sum of the sides of the squares of the sides equal the square root of the hypotenuse. And in fact, this theorem is, it goes both ways. So a triangle where the sides and the hypotenuse satisfy this relation has to be a right angle triangle. And that had applications. You go to the field and you want to measure land, or you want to get a 90-degree angle. You take a rope with 13 knots equally spaced, and then you go to the field and you stretch it, and you get yourself a 90 degrees angle. And in fact, okay, that's looks like a simple application. In fact, the Pythagorean theorem is one of the most applicable theorem ever, right? And whenever somebody measures length of anything in any coordinate field, velocity, coordinates, forces, more complicated things, we are all using the Pythagorean theorem again and again. If only they patented it, they could have enjoy from the royalties. However, there was one tiny problem that they couldn't solve. They looked at this triangle and they wanted to find C. So it's a right angle when the sides are of length 1. And by the theorem, it says that the square of C should be 2, so this C is the square root of 2. Okay, it's more than 1 for sure. It's less than 2 for sure. The universe is rational. Okay, so it's just a matter of time to find that rational number. Okay, they try 7 over 5. I don't know what they did, but let's say they did. They tried 7 over 5. That was off by 1%. They tried 17 over 12. It's close, but not enough. They tried another rational number, closer, but not there. But they were not worried too much. It's just a matter of time to find the exact rational number. And so one day, it was a beautiful sunny day in Greece. The birds were chanting, the philosophers were philosophizing, everyone was minding their own business. Dinner at a Pythagorean camp, they're sitting to dinner, just small talk, or maybe geometrical talks, I don't know what they did. And then Hippasus storms in, and he says, "You can't solve this." Silence. Silence in the room. Everybody stops eating. Pythagoras is the first one who kind of gets from the shock, and he says, "What do you mean? We are not good enough?" No. Hippasus says, no. You are the best mathematicians ever. No, but it's not that. It's even worse than that. No one can do that. Square root of 2 is irrational. Now, that was a big drama. In fact, this dramatic interlude is not only the dramatic interlude, this is the drama. Because, can you play it again? This is the ratio of square root of 2. These two notes, they give the ratio of square root of 2. So let's see the proof. Now, I know there are many mathematicians in the crowd, and they all know the proof. So I chose something which maybe not everyone knows. So here's a proof that square root of 2 is irrational. It's a geometric proof. So two possibilities for square root of 2. Either it's rational or it's not rational. And as we do in mathematics, we argue by way of contradiction. We want to prove that it is irrational. We assume that it is rational. We do some logical steps until we get a contradiction. And that means that the only possibility that is irrational. Okay, so suppose it is rational. And now let's square this, and we get that m squared is n squared plus n squared. And now, crucially, for this proof to go, there are many representations for rational number, as we saw, 1 over 3, 2 over 6. Take the smallest one. Take the one, m and n are dependent on each other, so take the one which is the smallest one. And so it means that there is a room of area m squared, a square room, and two carpets of area n squared each, and the area of the room is the area of the sum of the areas of the carpets. Okay, but they're not coming in a good geometric way. Anyhow, let's put them in. And what do we see? We see that there's an area which is not covered, but there's an overlap. It means that the overlap should equal the area that we didn't cover. So we have this equation. Now it's an exercise for you later on to check that indeed A and B are integers, because otherwise I'm messing around here. But this is a smaller solution. So we got a contradiction. So it has to be irrational. Now, that was a big crisis. They believed that everything is rational, and this square root of 2 now is coming from nowhere. And these things didn't go very well for Hippasus. I mean, the legend has it that he was thrown off a ship. But for the rational numbers and the irrational numbers, things went well. So very soon, other irrational numbers joined square root of 2. And more and more. In fact, this community grew so much that it was even larger than the community of the rationals. There were even more irrationals, after all. And they learned to live together in coexistence. In fact, they are very, very close neighbors. And they form the real numbers. And it's only with the real numbers that we can do we can do calculus, and we can do physics, which is our next topic. So now we are moving to strings and waves. So just to put some terminology, so a sound wave will be oscillations in the air pressure. So if I'm doing something like this, clapping my fingers, there's a pressure wave that travels across the room and reaches your ear. And that's one thing, but we are more interested for the purpose of this lecture, in musical tone, which are more periodic sound waves. And these have frequency, which is the number of periods per second, and they have a wavelength, which is the distance between crests, and they have an amplitude, which is the intensity or the energy carried by the wave. And thinking about how our brain reacts to tones, to musical tones, we are tuned to hear the ratios of the frequencies. So here is a simple melody that now Michel will play, and it has only 3 notes, so 3 frequencies. Michel, thank you. Okay, that's a simple melody with these frequencies. And here is another melody. So they sound similar, but not the same. Let's ask him to play them together. Again, together. It doesn't work. They're similar melodies, but they are not the same. Of course, they have different frequencies. But why do we say that they're similar? Because they have similar ratios. So the ratios between the notes that we play, they are the same. And we identify, we hear them as very similar melodies. And by the way, this translation of a melody to a point where it sounds the same, we'll call it transposition. Okay, and this is something which will come up soon. So now let's get closer into the question, why do tones which have rational ratios of frequencies, so now the frequency is reciprocal to the length of the string, so we can look either at frequencies or at length of the strings. And why do they sound consonant or harmonious? And for that we can choose many models, but the simplest one is the string, right? It's a one-dimensional physical problem. So let's just go a little bit into the wave equation. So we have a vibratory string, it's confined at the ends, and we want to understand the possible motions of the string. And so at the beginning, the string is at rest position, and then we pluck it, and then it starts moving, and it moves in time, but there's also a coordinate because every point travels differently, and we look at u will be the displacement from the rest position of the string. And this is governed by the wave equation. It's a second order differential equation, which I will not say more about that. It's just, it's the rate of the change in t of u, and it's equal up to a constant to the rate of the change in the position. Okay, and that this equation was discovered by D'Alembert in the early 700s. So I'm not talking about the equation, but I want to talk about the solutions to this equation. So firstly, it has infinitely many solutions. And these are it has pure solutions, which look like that. These are the resonance or kind of basic solutions of the equation. And you can see I have 6 of the infinitely many solutions. And you can see that they have frequencies. So the fundamental, which is the first one, has the basic frequency of it's called the fundamental frequency. And then we have a wave which has double frequency and triple frequency and so on and so forth. And these other solutions, they are called overtones. And they give all the solutions if we agree to take combinations of them. So every solution of the wave equation is a superposition of these solutions. So let's see how it looks. So here's from a different type of waves. What does it mean, superposition? The two waves, they ride on each other, and the amplitude is you add the amplitude of the two waves. And if we do this with the solutions to the wave equations in a string, then here's an example of taking two solutions, A and B, and getting A plus B. I can also, divide B by 5 and then add them, and that will be another solution. So here are two solutions to the wave equations. Any solution will be combination of these pure solutions. So now let's see why rational strings with rational ratios, they sound good. If I'm looking at the overtones of string of length 1, so these are the overtones, so the fundamental one, and then you see the higher one. I'm just freezing the time, just looking at a snapshot of these solutions. So when you pluck a string, it will, the vibration or the solutions will be combination of these solutions, where the energy will decay when you get higher and higher frequency. So the most of the energy of the wave is concentrated on the fundamental solution. In fact, you can now see what's the difference between two musical instruments that play the same note. So let's play, Michelle, can you play a middle A? And now Shubhadeep? And now Chantal? You heard the same A, right? But you could recognize, if I asked you to close your eyes, you would recognize who did that. And so the difference between the instruments is exactly the weights that you give to each of the overtones when you look at the solution. Of course, this is in real life. There's also the resonance box, and there are many parameters that control what you get in your ear. But the idea is that. So now, what happens when you do an octave and we take a string of half length? Well, we have the same solutions, except they have the frequency is doubled or already, and so when you compare the two, you see that there is all the overtones, including the fundamental tone of the half string, they are contained in the overtones of the whole string. Similarly, if you divide it by 3, then you see that again all the overtones of the sound that you get from string of length third, they are contained in the string of length 1. So this is the reason. There is an overlap between the overtones. They agree, and therefore we hear that. They sound good to us. They sound harmonious, which is what we call harmonious. One more thing that I want you to note here, there is direction here. The left side is contained in the right side. So later on, when we construct the circle of fifth and we'll need to choose a direction, how do we travel? We'll need to make a solution. The solution will be the direction that we'll travel will be dictated by the arrow going from left to right. We want to go home. We want to go to a place where all the overtones live. If I'm going from right to left, not all the overtones that I have from the right, I find them on the left. It's only all those on the left that are contained in those on the right. Okay, so that will give us a direction later on. And now let's zoom into a single string. So now what we'll do, we're going to prove to you that the overtone exists. So Michelle will play first a G with the whole sound. And now she will put her finger slightly on the string and she will suppress this fundamental tone. And therefore we will get the second one. So can you do it again? The first one and then the second one? So that's the octave. It's already contained in the basic sound. Let's do it with the guitar. Let's move to the third overtone. Let's move to the fourth overtone. And now we'll ask Chantal to press on this G3 on the piano and keep it there. And we'll continue with the overtones. Fifth overtone. And then sixth overtone. And now let's see what happens when we collect the last 3 overtones that we get. So you see the major chord is already built in the single string. The single string contains all these frequencies and contain the major chord. And so now what we're going to do, we are finishing now our second part of waves, and with whatever we have now, we can construct the equal temperament. So here's the problem, 2,500 real problem. We want to construct a finite system of tones. We don't want to carry, we can't carry a piano with infinite keys. It has to be finite. So we want a finite system of tones. And what do we want? We want it to contain the octave and the fifth. I hope I convinced you that we can't do without them. And the second thing that we may want is to allow any transposition, to be able to play any melody from any point of our system. We want it to be invariant under translation in terms of physics, but we want to allow any transposition. So now, we don't have to have these requirements, right? There are many tuning systems. They don't use this. That's fine. But what I'm saying is that if we want these 2 requirements, if we choose them, that will force us to do. That will force the solution. Okay, so that's a choice that one makes, and that is exactly the point where the equal temperament came to life, where this choice was made. Kind of these 2 principles, they wanted them to hold together. So let's start to work. Now we look at the first requirement, and we want the octave. So Sayantan, can you play the octave? And now we are adding the 3/2, the fifth. So now the first requirement is satisfied. Okay, let's move to the second one. But before that, let's make some sanity check. So the ratio from the first string to the second one is 3/2. The ratio between one and the third one is 2. And the ratio between the second and third is 4/3. And indeed, 3/2 times 4/3 is 2/1 is 2. So the multiplication of the ratios from the first and the second, and then second and third is 2. Okay, now we're moving to the red requirement. So, okay, we start with an octave, and now we want to add another string, another note. Where should we put it? Okay, we have a requirement. We want to be able to transpose. We want to be able to start a melody in the first string, and then be able to start the same melody in the second string, and so on. So it has to be the same ratio between the two. And okay, we need to solve equation, and that's r squared equals to 2. That's our good old friend square root of 2. So the ratio should be square root of 2. So if we do that, that's what we get. Sayantan, can you do that? These are the three notes that we have. And we are not there, because if we check now what's happening between the two, not working. And now, as we do a lot frequently in mathematics, we try small cases. So we try to add one more string. So I don't know, maybe there's no solution with 1, but maybe there's a solution with 2, maybe with 3, maybe with, I don't know. Okay, let's try another one. We divide it to add 2 more strings. The ratios are R, and R. What is R? Well, R cubed is 2. Then that's the cubic root of 2. And so, Sayantan, can you play C, E, G sharp, and C? So these are the 3. Can you play them one after another? So here they are. But if we now check what's going on with 3/2, we're not there. Okay, we can maybe try more and more and more, but who knows when that will stop. So let's change strategy. We'll come back to this later, but let's change strategy a little bit and do what the people who thought about it did. They started with the bass note, in fact, with the first requirement, and they just played with this until something happened. So let's do that. So we start with a string of length 1. That will be the C. We want to add the octave. Okay, we add the octave. Now we want to add the third. Now maybe we want to bring it down in an octave to put it closer to the other ones. So how do we take it down by an octave? We multiply by 2. So let's multiply by 2. And we brought it down. Now we can play a melody, C, G, and C, G. We could play this melody. Now we want to be able to play the same melody starting at G. Suppose I have some melody starting at C and going to G. I want to play the same melody starting at G. Now, C to G is 2/3, so I need another string which would be 2/3 of the G. So I need to keep going and add 2/3. All right, let's do that. Let's take an octave down. Let's take another 2/3. Let's take another 2/3. Let's take it an octave down. And now we want to keep going and keep going, but now we'll do it silently, and we do it without the numbers because it will. Oh, by the way, I'm starting organizing whatever we are building in a circle, because in the end it's going to be a finite thing. So we'll organize it in a circle. We're starting to build a circle which is called the circle of the fifth, right? From C to G it was 3/2 fifth, and then from G to D, and so on and so forth. Every step is 3/2 is fifth from the other. Okay, so we go on, 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 we go on. We're nearly there. Oops. It doesn't close. It doesn't close. It's like doesn't work. The 12th step is quite close to where we started, but it's not there. Okay, let's do a few more steps. Let's fast forward. So here's 12 more. It's just becoming worse. Let's do 12 more. It's just becoming worse. Let's do 12 more. It's horrible. So we have a problem. And the problem is that this process never ends. And now, why does it never end? Because the only thing we did is multiplying by 2 and dividing by 3 and multiplying by 2 and dividing by 3. So that can't go back to 1 because 2 to the m is even and 3 to the m is odd. Doesn't matter how much we try. It would just go on forever. And so the solution is actually lies in our imperfection. So our ear is not perfect. We can't distinguish between any two frequencies. So if we could just, it just passes a little bit. If we could just change the 3/2 to a slightly smaller number, then things might work. And that was a big, it's a big decision somehow to abandon the perfect fifth. That was a big decision, but you can compromise the perfect fifth, and then instead of the ratio 3/2 of frequencies, replace it by something slightly smaller, is less than 0.2%. And what is this A? Well, this A is the 12th root of 2 to the power 7. Okay, now where did that come from? So let's now revisit. Now that we have a hint where to stop. Previously, when we did this exercise with small numbers of strings, we tried 1, we tried 2, we didn't know where to stop. Now we have actually a hint where to stop. So let's see what happens if we take 12 steps. And we want, it's the red requirement is to be able to translate, to transpose. And so we have R times R times R times R 12 times. R to the 12 equals 2. And so we get the 12th root of 2, another irrational number. And now when we look at the 7th step, we get something which is less than 0.2% in the frequency, close to the rational ratio that we love, 3/2. And most people don't hear the difference. Musicians hear the difference, and sometimes with a violin and a cello, they even correct it when they play in a band. Of course, a piano can't do any changes, but instruments with continuous strings, they can just change it a little bit. But okay, we take this compromise and we just use it. And therefore, what did we do? We took our original requirement, we loosened it a little bit because we understood by the 3 to the n, 2 to the m, that they are never equal, that it will never there's no solution if we don't compromise something, if we don't relax the requirement somewhere, nothing will happen. So we almost take the 3/2, but we allow any transposition, and we get the equal temperament. Let's see. 3, 4. Thank you. That's it. We have the equal temperament. We can now take a break. I think we'll take a break of maybe 12 minutes. That's the correct number in this lecture. And we'll continue, and then we'll do more music. We are going to focus on music. Sorry? Yeah, we can do the sequence, but remember my comment earlier that yeah, ask so that everybody will hear. You want to hear everything again? Okay. Yeah? Okay. Ready? Okay. And in the second part, we are going to do two things. First, we are going to look at the possibilities or the beauty, I should say, of the pre-equal temperament. So before the equal temperament, they did the 3/2, pure fifth. Of course, if you try to close the circle, there's a problem. So this is F sharp is not equal to G flat for musicians. That's the clash. But so they just used this part, that the whole music was based on half of the circle. So we're going to look at a few things, what we can do with the half of circle, and then we'll jump to the equal temperament, and we will see kind of what possibilities the irrational ratios kind of give us, mainly in jazz. And of course, not only, but it's a choice, yeah? Okay, so as promised, let's go back to the pentatonic scale.
Regardless of where I am, anywhere, every audience gets that. But it doesn't matter, you know, it's just, you know, the pentatonic scale for some reason.
So what is the pentatonic scale? We take the first 5 steps in our, when we build the maybe also take this one down. We look at the first 5 steps, and then we condense them into 1 octave. And these are the 5 notes that we get. And Michel will now demonstrate what you can do with it. So it's absolutely natural, because the 3/2 is natural, it's in the string, and you only take the first 5 steps. So it's the most fundamental thing that you can do. And Michel will now demonstrate what you can do with the pentatonic scale. Beautiful, thank you. Now let's add 2 more steps. And we get the white keys in the piano. So there is a historical reason why we have the white keys on the piano, because if you do the first 7 steps, that's what you get. If you never in your life move beyond that, you build your keyboards only with these notes. Then one day you decide to add F sharp, more notes, then you have to bring in black keys. Otherwise, you need to rebuild your instrument. So these are the 7 steps. First step. These are all the white notes in the piano, and Michel will play something with that. Thank you. Now let's revisit the harmony. So we observe that the major chord is already in one string. One string knows the major chord. It in fact knows much more. So let's look at the harmony. Now remember I mentioned that there will be a choice of direction. So we need to travel in the circle of fifth, and we need to decide it's not actually that we need to decide. Our ear decides for us. There's a natural direction, and the natural direction is going home. So you move from a string with some harmonics, some overtones, into a string that contains all those overtones. So this is when now we're going counterclockwise. When we built it, we went in the clockwise direction. So here's the most fundamental harmonic progression. Harmonic, it's not even a progression, just two chords. We'll go from G to C. 3, 4. So this is what happens when you go from G to C. Now let's start in the D minor, and let's see what happens if we do 3 steps. 3, 4. It's just flowing with the circle of fifths. Let's be adventurous. Let's take another step. 3, 4. Thank you. Let's do more. Now let's just do one of the Baroque progressions. We only use half of the circles, and earlier we started in A, moved to D, C, and G, but now let's just follow the circle, the half circle. So here is one of the many Baroque progressions. 1, 2. They're starting at E minor and then going up. 1, 2, 3. Now, let's jump 200 years forward, and I want to show you that good things, they stay forever. And we are going to use the same progression with Autumn Leaves, composition from 1945. But before that, we're going to do 7 chords. So these are chords with 4 notes. So what is this all about? So now I saw your talent, I'm becoming more greedy. So let's think 4-part harmony, yeah? So let's sing a chord, a 7 chord. So we'll split in 2, and then there's a path over there. So that will be our 4 parts. And please join me. Ready? Let's see. Pa, 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 pa. Together. Ba, 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 ba. Bravo. I think start packing for a Europe tour. So let's see, let's hear Autumn Leaves. 1, 2, 3, 4, 1. Thank you. Now, there are many, many standards, jazz standards, with this progression. Here's another one. We'll just play the A part of Fly Me to the Moon. 1, 2, 3, 4. Same progression. Started at E and traveled in this half circle. All right, now we are jumping to the equal temperament, and let's see what can we do. So the first thing that we do is we're going to be a little bit naughty. We're going to take the pentatonic scale, minor version. So Michel, can you play this scale starting from A? So it's the same pentatonic scale, just different starting point. And now we are going to go to the other side. And we are adding the E flat. And we are getting the blues scale. So here's an equation. Pentatonic scale plus square root of 2 equals the blues scale. So now Shubhadeep will play the blues scale. Thank you. And now let's play a little bit with symmetries. So the point is that now we are in a symmetric situation. We have a watch, 12 hours, and equally spaced. This thing has symmetries. To begin with, it has rotational symmetries. Before I'm doing anything with symmetries, I want to move from the circle of fifth to the chromatic circle, which means I'm taking antipodal points and I'm flipping G with D flat. So every other hour, I'm doing a flip. So the circle of fifth now becomes the chromatic circle. And now the circle has symmetries. We have rotation symmetries. So we can rotate in 30 degrees. And what happens if we just roll over this circle? Sayantan will play a chromatic scale. Thank you. Now we can, another symmetry is to jump in 60 degrees. So what happens when we do these jumps and we look at this symmetry of the circle? Thank you. That was the red one. It's a whole tone scale, and we can also play the yellow one. Thank you. We can also do a 90-degree symmetry. And yeah, let's hear this as arpeggios. So it's just going over these corners of the square. But now the points are far enough that we can actually make a harmony out of that. We can play them together and we get a diminished chord. And now we can descend and move to the next one, rotate it, and then rotate it, and then rotate it, and then rotate it, and keep going, keep going, keep going. These are all symmetries of the circle. Thank you. So these were rotational symmetries, but the circle has more symmetries. Anyone want to help me? Reflection, right? Let's see what happens when we reflect. So let's revisit our harmonic progression, but now use some reflections. So here is a D minor chord. It's D, A, and F. So let's hear it. And now reflect on the diameter, and now let's reflect again on the G. Let's reflect again on the C. You see the harmonic progression that we had before is actually coming from symmetries of the circle. We were here, and now we are here. That's a déjà vu. So we can keep going. So why don't we? 1, 2, 3, 4. Thank you. Now let's add 7th. 3, 4. Thank you. So that was a small tour in the symmetries. And now the last piece that we're going to play here is the most involved one. So this is really a giant step. So giant steps, this is a tune composed by John Coltrane in 1960. And this tune uses the circle of the fifth and its symmetries and the equal temperament to the full extent. So that's what we are going to do now. That's a big challenge, and I admire them for jumping on the challenge. And yes, they did it. So this is really difficult. So first, let's just play it. So let's hear it. 1, 2, 3, 4. Second line. Third line. Fourth line. Again. Thank you. So now I want to show you so that you can see what you just heard. But before that, I want to invite one more musician. Unfortunately, he passed away, so we have only recordings. So this is Barry Harris. He passed away 4 years ago. An amazing piano player, teacher, composer, and this is taken from a workshop that he did. You can find 15 minutes on YouTube. That's the whole. That's the recording that I found. So this is a snapshot from that workshop, where he explains what's going on with giant steps. In fact, he doesn't know it. Yeah, and you will see he doesn't know it, and he learns it as he explains it. But he has it. He has it here. He just need to put it in his fingers. He's doing it. He's doing it very quickly, as you will see. So let's see what Barry Harris is doing.
I don't even know the song. No. Let's see. Where did I go next? How do I do this? Let's get this song. Show me the song. What? Then that's it, right?
1 minute later.
Well, I almost played it, didn't I? That's the first time I ever tried to play it, because I never wanted to learn the song.
Okay, let's help him and let's analyze the tune. We are going to look at four motifs, four themes. So one of them is the harmonic anchor of this tune. So you can see 3 chords there: E flat major 7, B major 7, G major 7, and going back to E flat major 7. So 3 chords. If we look at the circle of fifth, they nicely spaced in the circle, very symmetrically. And so let's just hear this motif. So it doesn't exist, right? You saw I cut it in the wrong way from the chart, but let's just think about this and let's listen to this. 1, 2, 3, 4. Thank you. Of course, they can go on forever, right? And you couldn't tell because it's just everything is symmetric. The second motive is to look at the progression in the first 3 bars. And now we rotate the triangle and we start again at the B, but then we follow the contour of these 2 triangles together. 1, 2, 3, 4. Thank you. So this is a drill. This is only part of it is written. Actually, the 2 parts are written, but they are written in different places. But we wanted to look at the symmetry and show how it's built. Third motive is these 2-5-1s called in jazz from 5 to 1. This basic progression that we've met earlier. Let's see it here. So now we rotate the triangle again, and now we start at the A minor. And we'll just slowly play the chords. 3, 4. Yeah, we already met this progression. Now we jump to the F minor 7. And now we jump to the other side. Last motive, we'll look at these two bars and let's see geometrically how it looks on the circle of fifth. So we start with the E flat on the left side. That's the kind of the naughty crossing that we did before with the blues. And now we start with the A flat and then move to the other side. And then let's do it again. We start with the E flat, 3, 4. Then we move to the other side. That's it. Okay? Now these four motives, they give everything. Now let's see how it goes. Ready? 1, 2, 3, 4. Other side. Other side. Other side. Other side. Other side. Thank you. Let's see what Barry House did in the meantime.
It's like you got to really make it. I want to hear it melodic.
And that brings us to the end of the lecture. Let me remind you, we were after the equal temperament. We wanted to understand why there are 12 tones, so 12 notes in our system. And the answer is that this is a unique meeting point of 12 rational ratios and 12 irrational ratios that are close enough because our imperfection. And the rational ratios, they give us the harmony, they give us the chords, they give us, and the irrational, the fact we ended up with irrational, that give us the transposition, the symmetry, and the flexibility to move with the harmony anywhere we want. So thank you very much. I'd like to thank, special thanks to Disha and the ICTS outreach, and to these wonderful musicians that jumped on board. Shubhadeep, Michelle, and Sayantan. Thank you. Now we have time for questions.
Please raise your hands. We'll bring the mic to you.
What about drums? I mean, do they follow the same? Drums does it follow the same 12 note? I guess what I'm trying to say, does it follow the same as the other instruments?
Yeah, that's a great question. So the drums, so it depends. When you're playing on a drum kit, then it has vibrations. It's a two-dimensional model. It has resonance frequencies, but it's different. The solutions are different, and somehow they don't give you a clean frequency organized in a way that help us to do things. but still you can, there's a fundamental frequency, and sometimes you can tune the drums. For example, if you look at timpani, then one does tune the timpani. There you get a cleaner sound, and the timpani you tune them, and you get a more kind of decisive frequency. And of course, also, it's not exactly your question maybe, but there are percussions. So you have marimba and xylophone. So there are other musical instruments that use kind of different, not strings, but use. Yeah.
I just sorry.
Indian tabla. The
Yeah.
tabla that gives a pure note. That's because of the way it's sort of weighted.
It's weighted, yeah. That's right. So the tabla is super complicated.
That's right.
That's
Black
right.
spot is very important.
That's right. Yeah. That's right. Yeah.
Hello. Can I ask?
No, actually, I wanted to say the same thing that Spenta already said. That tabla is an example of a tonal drum.
Yeah.
Because of being weighted.
Yeah.
Person over there.
Right. I had a question. When you show the circle of fifths, what I learned in music theory is that when you progress along the circle of fifths clockwise, C has no sharps and flats, G has one sharp, and then D has two, and then A has three, and so on and so forth. But interestingly, what I saw there was C, G, D minor, A minor.
Yeah, no, good question. So when I wrote this, there were different circles all over the place, but with the first one that I did, there were no minor, it was just the note. But then I wanted to put some harmony, say in giant steps. Yeah, or something before. So here there are no minor or anything, it's just the notes. But you can choose any of your notes and play any chord on that based on that note, even if it's outside the scale. So you're absolutely right. If you want to play just the scale of G, then you do what G tells you and you put one sharp. But you can imagine that on G you decide to put another chord, G minor, and you'll have a B flat there. So whenever I put chords there, it was just with relation to the specific tunes that we played. So if we played, I don't know, Autumn Leaves, they play Autumn Leaves, then at each point there was a chord.
That was a departure from the diatonic chord progression, or was it the same?
It was a chord built on the scale that you think. So yeah.
Okay.
Yeah.
Yeah. Can I ask a question?
Yeah.
Over here. Yeah. No, you mentioned that the difference between F sharp and G flat is 0.02%. Right? Yeah.
Yeah.
And for low frequencies below a kilohertz, even in principle, one cannot tell them apart unless the note is long enough, like more than 2 seconds.
Yeah.
Yeah. So I'm just making the point that even a practiced musician cannot tell the difference for short notes.
That's right.
There's a question here.
I'm asking this question at the cost of being laughed at by the entire audience. Is there any similar analysis of whether the birds, such as quail, also have some frequencies being used, or they're used randomly when they start calling?
The birds?
Yeah.
I think I'm not qualified. I'm only a mathematician. I don't know. It's a great question, but I don't know. I don't think it's a great question. Yeah.
Okay.
Question there. Yeah. Hi. Thank you for the lecture. It was really wonderful.
Thank you.
I was wondering. It's a bit of a physics question, but when you combine different frequencies, that sort of gives you a note, right?
Sorry, I didn't get that.
When you combine different individual frequencies, that gives you a note.
It gives you. Well, it depends if the frequencies.
Certain, like if they're in certain ratios, right? As in a note can be broken down into a sum of those frequencies.
So by a note, we just, Sandal, can you press A? So here's a note, yeah? That's a note, what we would call a note, but it has a base frequency, that's what we hear, I don't know, 440 hertz for A, and then it contains the overtones.
Right.
So I would call a note the collection of all those frequencies somehow.
Yes, yeah. So so my question is, it's not exactly a linear combination of all those frequencies, right?
Oh, it is.
Oh, it is?
It is. So you look at the vector space of functions on the interval, which is the length of your string.
Right.
And
So
you look at the space of continuous functions, right? Because when you pluck the string, it stays a string. It doesn't.
Right.
And so you can write down the Fourier expansion of that continuous function, and these are the harmonics. These are exactly the harmonics. This is the Fourier expansion, and it's a linear space.
Right, but so now I'm wondering where the irrationality comes in.
The irrationality comes in when you take different notes, you want to combine two sounds, two tones, and if you want to build a system that is invariant under translation, in the sense that you wrote a melody and suddenly the singer that comes to perform with your melody, her voice is higher. So you need to shift everything up. So we want to be able to do this translation. And to do this translation, transposition, and keep the harmony, these are contradicting requirements. So that's the reason why the problem wasn't solved for so long. You need to make this compromise. You need to decide that you give away the perfect 3/2. And as every violin or cello player will tell you, in the band, they will slightly fix they will do it perfectly. They don't want it. So it was very difficult to give up on this kind of perfectness.
Sorry, just to follow up. Is there a relation between some things we consider perfect and irrational things? For example, a circle is perfectly round, but the constant associated with that pi is irrational. And similarly,
The
pi, which is associated with the circle, is irrational.
Yeah.
So is there a relationship between what we consider irrational versus what we consider perfect?
Well,
is there some kind of connection?
Irrational is also perfect.
Yeah.
I would argue. Yeah, these are perfectly good numbers. Yeah. And also I should say, no one ever on the planet, in the past, in the present, in the future, will measure any quantity which is irrational, because any measurement that we are doing has an error. And so it is in our mind. All this discussion is in our mind. We are playing with things, but nature has its own opinion. Yeah.
I wanted to ask you about two compositions of Bach, Well-Tempered Clavier and Art of Fugue, if you can say a little bit.
Yeah, so somehow as I said, I'm not giving an historical overview, so I don't know when exactly the equal temperament kind of everyone used it. It was a process, right? There was no Google. They had to travel with their instruments. So at some point they realized that they want the equal temperament, and somehow to celebrate that, Bach wrote this wonderful kind of 48 preludes, fugues, minor, major, just to celebrate and to show that you can write down in any key. There's a complete freedom now. You have your piano. It's not like the harpsichord where you needed to press certain buttons in order to adjust, because it wasn't equally tempered. Now they had the equal temperament, and so you can play any melody in any key. So kind of that was the point in Bach's composition.
Thank you.
So, sorry, I'm not an expert, but it looks to me like all the strings on the cello are the same length.
Yeah.
So there's something. So there are other things going on than just string.
Yeah,
length,
they have
right?
different thickness.
Okay.
They have different thickness. Sorry? Yeah. Yeah, they're not this, but this is not a big difference, right? They are thicker. So these are different materials, right? So when you solve the wave equation, it depends it depends on the material. So it could be different material, it could be different thickness, it could be different. Yeah. So that's the.
I don't know if this is relevant, but we did not go to transcendental numbers beyond irrational. Is there anything like that?
So the irrational numbers, we have two types of them. We have something like square root of 2, which is a solution of a polynomial equation, and the transcendental like pi, but they are all irrational, and they are all fine. So the irrationals, they contain the transcendentals, they contain. I'm not saying that there are no other numbers in the universe. They're the complex numbers, but they're in our mind. So the real numbers, it's the rationals and the irrationals. And the irrationals, they are algebraic, square root of 2, they are transcendental, pi, e, and other numbers.
Whatever we discussed today applies also to transcendental.
It apply. Well, I don't know everything, but for the equal temperament, you only need roots of 2, only roots of 2. But yeah.
I have a comment. Hi.
What?
It's here.
Yeah, sorry.
I have a comment actually. So since you're delivering this talk in India, I'd like to sort of point out that the ancient Indian mathematician Bodhayana was amongst the first actually to state the general statement of what is called the Pythagorean theorem centuries before Pythagoras actually.
I read about that, yeah.
Okay.
So thank you. So do you know the exact year?
Yes, it's 800 BCE.
Yeah, so I think maybe I'll fix my slide in the future. I agree. I chose this as a kind of as an anchor.
No, I understand.
But you're absolutely right, and this is what I said. Many things happened. So
Yeah.
the whole thing with the Pythagorean, and it happened in other places in the world, and I know about India.
Yes, and
you're
also about
absolutely right.
our logo actually is a visual proof.
That's right.
Of the due
Here's
to
a proof
Bhaskara
of
the
the
second.
Pythagorean theorem. Yeah.
Yeah, 12th century.
Yeah. Thank you for that.
So there are these music systems with different number of notes, like 22, 24 kind of. So what kind of symmetries do they follow?
If you add more notes,
I'm not sure what they do, but there are 22 note systems.
Actually, they are called Shrutis in the Hindustani classical. They are called Shrutis.
Yeah.
They're almost, they want to catch the continuum as much as possible. So there are these Shrutis they add in Hindustani class.
Yeah, so yeah. So what I want to say is I didn't get to show you. That's when you're leaving. I'm playing something for you, and that's a blues of Wynton Marsalis and a band from the area from here, where you can hear somebody improvising with quarter notes and with a flute and kind of instruments that play different things. So I'm not absolutely not expressing an opinion about the preference of any system. It's the things that you can do with a continuum and with other there are other choices that we can make and other principles that guide us. After all, music, we are imitating vocal. Any instrumental music is imitating our vocal chords, and so we can do many things. And even historically, there was an evolution of different uses and meaning. What does it mean to go in a rag? You will have different meanings for the quarter notes. So absolutely, this is not. I'm not saying anything about that. I'm just saying that if one wants a system which is invariant under translation, that you can play any melody from any point and contains the fifth and the octave, then you have to have these 12 notes, but now you can have more. You can have more based on, or you can have the continuum even. Yeah, so sure.
Yeah, sir. So actually in the problem statement of finding the equal temperament, one of the one of the requirements was that it has to be 3:2 ratio. And the reason behind it is it sounds good to us, right? So if say we were a different species and some other ratio sounded very nice to us, like, or is there something very fundamental about the number 3:2?
Yeah, so great question. So I think now I'm just expressing an opinion. There's no answer. So why do we like this 3/2? We have in our eardrum we have a membrane, right, and it vibrates, and we get a pleasant feeling when the sounds are consonant or harmonious. Yeah, when the frequencies are 3/2, there's some pleasant, relaxing feeling. Like listen to, can you play C and G? And now C and F sharp. So this is both interesting, right? One is relaxing and one is creating tension. Now tension is not bad, right? In life we have tension, then we relax. Actually it's good, these fluctuations, they are good. So when we want this tension, we can have this tension, but the fact that we feel that it's pleasant to hear this 3/2, it has to do with the structure of the frequency in the membrane. So I would imagine that the answer would be yes. They will have a similar system if they solve the same physics, right? It's all about solving the wave equation on the string.
But is it possible that they will end up with a different set of, another species will end up with a different set of notes, which may not be 12?
Yeah. What about? Dolphins and birds, yeah.
Dolphins and whales, do they use the same notes?
Anybody here maybe can help me out?
Because they're intelligent species too, right?
Yeah.
I mean, birds, compared to birds, they are astoundingly intelligent. So.
I will have to prepare myself for the next time I give this lecture with all these clever questions. I don't know.
We'll take 2 more questions before we wrap up. 2 more questions?
Somebody there asked about the length of the strings, and I have a similar question. If you look at a bass instrument versus a more treble instrument, the scale length differs. So the distance you need to travel one semitone in a bass instrument is longer than in an instrument tuned at a higher pitch. For instance, even in a guitar, at the lower frets, the distance between a semitone is larger than at the higher frets. So what's the scientific reason behind it, to put it very simply? Yeah.
The physical distance is different, yes, but the ratios are the same.
And what's the reason for the physical distance being different? I know it's a very... I mean, I'm not a mathematician.
So I don't know. I never looked at the geometry of a guitar, but the point is that whatever the distance are, they produce the same ratios of the kind of ratios which are we keep the ratios. That's the whatever happens there in the guitar reflects that. So I need to look at the guitar itself and look at that string and look where it starts. But we can do this together if you want. But that would be my answer. Why? Yeah. Yeah. I choose the kindest person that agreed to come and play with us. That's my answer. Yeah. It was just there. We can do it with any instrument, but you cannot do it without Michel. Sorry? Yeah.
Yeah, there is one last question.
Yeah. Do different genres of music choose different progressions, or is it completely genre agnostic? And what is your favorite genre?
Yeah, so different genres, they use different progressions, but they all kind of follow very similar patterns. Yeah, you could. I think I'm just scratching in maybe a second version or a second part of this lecture. One can go more into the harmony and see more relations, because we just scratched the beginning. So yeah, there are many kind of progressions, and there are many things in the circle of fifth that are kind of built in the way we think and the way we feel and the way we want to hear, but you can just move them around in a very creative way and get the similar effect. Yeah. All right. Thank you very much, and good evening.
I just before just wanted to thank Uri again. I was going to say a very enlightening lecture, but it was more like an end-sounding or end-listening lecture. But thank you so much, and just as a small token from ICTS for your wonderful lecture.
Thank you very much.
Disha will also give a little token to all the musicians.
Thank you.
Thank you for taking the trouble and giving such an informative and wonderful lecture.
Thank you very much, and thanks again for these wonderful musicians, Michel, Shubhadeep, and Sayantan. Thank you.
Yes, very good. Those of you who came by the BMTC shuttle, it will leave sharply at 6:30, so please go towards the main gate. The shuttle will leave to Sandal factory, and those who haven't registered, please don't take the shuttle because it's already full.